Okay, class, we have got to get into a very involved subject here, and that is dealing with osmosis and osmolality. So you got to really put your thinking caps on, and you're going to have to kind of read and try to understand this. I'm going to do the best I can to explain it verbally as I can. Okay, this right here is a handout in the Word document, MS Word document, called Osmotic Pressure Handout New. Osmotic Pressure Handout New. And that you'll find. You can read on it. Now this gets a little more detailed than I want to get into, but I've got certain excerpts. But you can always look at it. It's in that ANP2 section in my private website. All right. Now let's see what's the importance of this. Okay, we're dealing with the kidney. And the kidney we've been talking about can dilute and concentrate the urine. And this all has to do, the effort has to do with its determination of blood osmotic pressure. So that sets the stage. So let's look at what I have here to kind of set the stage as we talk about osmosis and osmolality. The osmotic pressure of the blood is somewhere between 270 and 300 milliosmol. The body, as you know, is mainly water, about 56 to 60%, and actually more in some cases. As important as water is in the body, and the large amount, as important as water is in the body, and the large amount there are no water meters in the body. Now that's a lot of water, but there's no way for the body to determine how much water. Well, how does it do it? The body water volume is indirectly determined by blood osmotic pressure. Let me say that again. As important as water is in the body, and the body has the majority of the body is water, there's no direct determination of water volume in the body. It is indirectly determined through osmotic pressure. Okay? Important factor. We have osmoreceptors in the hypothalamus of the brain that's looking at everything. The kidneys mainly and sweat glands are the major controllers of the blood osmotic pressure based upon how much water they put out or how much water they retain. Okay, we're going to do some more on this, but I want to show you the significance. Now what I want to get into is understanding of osmosis first, which you should have gotten in ANP1, but let's take a gander at this. All right. What we have is, we have these things called passive transport, AP1. Passive transport had three things. First of all, passive transport meant the particles were moving under their own energy. The particles were moving under their own energy. That's passive transport. They needed no additional energy. Okay, let's see what I had up here. Okay, nothing there. The three types. Now this PowerPoint here, let me kind of tell you what this is. This is an ANP1 section, and you can always pull it up. It's called the cell. This is an ANP1 section. It's called the cell, if you want to pull this one up sometimes, because you have access to all of my stuff. All right. So we're looking mainly at diffusion and osmosis. Okay, let's go to the next one. All right, so diffusion, I'm going to say, is the net movement of certain particles from a region of high concentration of those certain particles to a region of low concentration of certain particles. Now, unlike what a definition in the textbook which would say, diffusion is net movement of particles from a region of high concentration to a region of low concentration, that's not exactly right. What happens is, and I want you to listen to me carefully, particles look at their own kind. Particles look at their own kind. So even when particles are in a mixture of particles, they look at their own kind. See, that's the rationale why we could do the partial pressures. Remember in the respiratory we did the partial pressures? That a gas and a mixture of gases would exert a pressure independent of the other gases in the mixture. So this diffusion is true for gases and liquids. You should know that already. So particles look at their own kind when moving. Particles bounce around randomly by entropic motion, entropy. They bump into one another like people moving in a crowded room. They wish to get hit less, so they bounce in the less crowded room. They go from a high density, high concentration to a low. Okay, let's go a little further. So here's my example. Here's a compartment. Let's say we got this on one side and this on the other side. And we're looking at diffusion. We have 4 A's on this side, 2 B's, 5 C's, 3 D's. This side has a total of 14 particles. This side has 11. Okay? Now, dealing with the textbook, it would say, well, this side with more particles would move to this side. That's not exactly true. Okay. What it is the A's, there are 4 here, would primarily go this direction. Now, some will come back this direction. See, these particles don't have a brain. So if they bounce over here, they'll bounce back this way. But that's where the net movement comes in. Net means to subtract. So there's a net movement in this direction because there are 4 going this way minus 2. So the net direction is this way for A's. For B's, though, check this out. It's in this direction. See, particles look at their own kind. For C's, in this direction. For D's, see what I got? Okay? So what happens is basically that particles move in accordance with their own kind. They move in accordance with their own kind. Okay? Everybody okay? Right? And actually here on D's, I should have shortened that arrow, shouldn't I? I should have shortened that arrow, bring it over some, because it's actually more going this way. Well, should have, okay, because 3 and then 2. All right, let's go a little further. When the concentration of the particles on both sides is the same, that particle movement is in one direction same as the other. You've reached equilibrium in diffusion. Now, technically, once you reach equilibrium, the particles are moving equally in both directions. Equally what? In both directions. So when you reach equilibrium, technically diffusion has ceased. Now, technically diffusion has ceased. Why? Because if diffusion is a net movement, you no longer have a net, because subtracting one from the other equals 0. But the particles will do that, but they all are looking at their own kind until they reach equilibrium. Okay, that's diffusion. Both sides, such a one direction, this is equilibrium. Okay. Now, right here's another example of this. You can glance at in that cell PowerPoint. All right, now we get to the subject at hand, osmosis. Osmosis is what I'm going to call a prejudicial process. And let me tell you why. Because you're giving favor to some particles and disfavor to others. You're giving favor to some particles and disfavor to others. So osmosis is the net movement of certain selected particles from a region of high concentration of those selected particles to low. And this is where the prejudicial part, through a membrane primarily permeable to those certain selected particles. Let's put selected. To those selected particles. Okay? So what you have is, you have now given these selected particles favoritism. The others are held back. Now, I go here. So see, this barrier is blocking these others. Assume only that these particles can move. Now, this is where the clincher is going to come in. The clincher is going to come in that since particles look at their own kind. Let's go back to it. Since particles look at their own kind, if you allow these C's to move, they gonna do it. They don't really care about these others being blocked. These C's are going to reach their equilibrium. these C's are going to what? Reach their equilibrium, regardless of the others being blocked. All right. Now, let me show you what's going to happen in this particular deal. Here is an example of osmosis. Here's a membrane permeable to water. Okay? Permeable to water. Now, if you notice, I'm going to go back to my definition of osmosis. Just thought about that. In a textbook, it would say net movement of water particles from a region of high concentration of water to low. If you notice, I didn't put water. I said selected particles. The reason is the term osmosis comes from chemistry, not from biology. Biology says water. Chemistry says selected particles. Why? The only reason biology does it because most of us are water. Okay? But that's not the root word. That's not where it came from. Now, I want you to draw attention to this. This membrane is freely permeable to water, not to these solid particles. Look what happens. Water reaches its equilibrium. That means, notice the higher level of water on this side. Now, you would think, okay, dang, how could it be higher on this side and that side, and you got a membrane that's letting stuff through? Because water seeks its own level. It's the selected. It's the one that the prejudice selected for. So it goes ahead and does this thing. That means now water is higher on this side than that side. Strange as it might seem. Now here's where the clincher comes. That means that water has a stronger effect now. It has a pressure. Now here's where the clincher is going to come. Osmosis exerts a pressure. Diffusion does not. Listen to me again. Osmosis exerts a pressure. Diffusion does not. Why? Because in diffusion, there's no prejudicial process. Everything reaches its own level. Therefore, equality would occur. But with osmosis, since you're giving one thing advantage over the other, it goes ahead and seeks its level. So osmosis exerts a pressure, diffusion does not. Now, how much pressure, using just this, does osmosis exert? If you were to take something and push the water level back down. Now think about it. It's almost like getting on a bathroom scale or scale. What do? You change the weight to counterbalance you. Whatever you had to change the weight to balance you, that's your weight. So if I was to push the water level back down where it's all equal, that would be the amount of pressure being exerted. If I was to push the water level back down to where it would be equal, that would be the pressure exerted. And that's what we would call the osmotic pressure. You see? Right? Just like this here. Okay? So then we can come to some terms dealing with osmotic pressure. If we had two solutions side by side, and one had more solute than the other, the one with the solute would be hyperosmotic. See, the osmotic pressure is being determined by the solute concentration. Let me say it again. The osmotic pressure is being determined by the solute. The higher the solute concentration, the more the osmotic pressure. Okay? If both sides have the same solute, then it's isoosmotic. Now, if we're dealing with a container that can stretch, like a cell, then we use the Latin word tonus to stretch. Then we can use these terms, which are the clinical terms, hypertonic, hypotonic, isotonic, which is synonymous with this. Now, in ENP1, you should have learned that a red blood cell is isotonic with a 0.9% sodium chloride solution. That, in fact, is what we call normal saline. Normal saline. Okay, we're going to close this video. We're not through with osmotic pressure, and then we're going to start another one. Continue right on.